This video is about molarity and dilutions, which should be mostly review because you should already be able to define the words concentrated and dilute and calculate the molarity of a solution. And at the end of this video, we'll review that and calculate molarity with dilutions to explain dilution steps in very close detail. So the question of the video is, imagine each ion represents a mole of particles. So where you see 3 Na pluses and 3 Cl minuses, imagine that's like represents 3 moles of them, just to make it a larger amount, because 3 wouldn't be something that we can actually measure because they are not drawn to scale, right? And so there are 3 moles of NaCl dissolved in that water, and it has a total of 275 milliliters, if you can see in the picture. So first, we want to know how concentrated it is, so how many grams of NaCl were added to get to that solution, how many particles are actually in that solution, and would the same mass of sugar, C6H12O6, be added to that equal volume of water, 275 milliliters, to acquire the same concentration of sugar. So to get back to that, we have to define some terms. Solutions are homogeneous physical mixtures, which means I can't see the parts, but we know they're in there because of either the color or the smell or the taste. And they should be 2 or more pure substances. They should be transparent, so maybe it might be reddish color, but I can still see light coming through it. And they'll pass through a filter, so filtration won't be enough to separate them. In a solution, the solute is dispersed universally through the solvents. So again, it's dissolved perfectly and uniformly to some extent. So it's not more concentrated in one area than another. The solute is the minor part that's getting dissolved, and the solvent is the major part that's doing the dissolving. And water is a universal solvent in that it dissolves things that are polar like it, and sometimes it dissolves some other substances like ionic compounds and so on. So you see water as a very common one. Aqueous solutions were the ones that are water solvents, but not all solutions have to be aqueous. So again, the solute can change phase in order to dissolve, so it can go from a solid dissolved into water, for example. Now it's aqueous. It could be a gas, like carbon dioxide dissolved into water. That's how you get like bubbly water. But it could also have been another liquid that dissolved in order to get it to be a solution. Solids and gases can also be solutions. Like the air is a solution. I can't see the parts, but I know it's made up of things like nitrogen and hydrogen and water vapor and oxygen. And then other alloys like steel or brass or jewelry, they're mixtures of metals, but you can't see each metal individually. Concentrated means solutions contain large amounts of solutes dissolved in, and dilute means it's mostly water or large amounts of solvents, less solute. So if you look at the 2 iced teas, since the one on the left seems to have more sugar dissolved since it's darker, we would say it's concentrated, and the one on the right would be more dilute. Molarity is one way we can measure the concentration of a substance, specifically the amount of a substance in a solvent is their concentration, and molarity is one that we use most often, where it's the moles of the solute in a liter of solution. So generally last year we used to use the big M to represent molarity. You might also see it as moles per liter, or moles per liter, and the liter says -1 because that means it's on the denominator. So if you have a problem with that, make sure you take a note of it and ask me about it in class. But molarity, again, is just one type of concentration. We also talked last year about percents and parts per million, which will come back later in the year. So again, molarity is the moles of the solutes that you're dissolving in liters of solution. And because the volume is temperature dependent, if it's hot, the volume usually swells, and if it's cold, the volume usually contracts. This molarity can change with temperature, so it's something we have to be aware of, that if we measured a solution in terms of molarity, we have to keep that solution at the same temperature all the time, which can be kind of hard in our science classrooms. Here's some examples of molarity that we should be able to do without a calculator if it's in a part 1 of the exam. If 3 moles of sodium chloride is dissolved in 6 liters of water, what's the molarity? That means it's just 3 divided by 6, which should be a half of a molar. And if you want to do sig figs, since there are 2 sig figs in the previous questions, we're going to keep 2 sig figs in our answer, 0.50. Or if 29 grams of sodium chloride are dissolved in a liter of water, what's molarity? So we have to look up how much sodium chloride weighs in the reference table, which is 58. That's half of the mass that we have, so half of a mole is present in a liter, so it's also half of a molar, right? So this is just showing you can get concentrations that are the same, 0.5 molar, 0.5 molar, but get them in different ways. In the first example, we had a 6-liter container. In the second example, we only have a 1-liter container. So you're dissolving different amounts in order to get the same molarity. These examples are harder and they might either need a calculator or be estimated. So number 3, 100 grams of KF are dissolved in 300 milliliters of water. Notice the decimals make those zeros count. What is the molarity? So we're going to have to look up how much KF weighs, which is 58.1. It's about 2, but more specifically, it's 1.72 moles. And we're going to have to change those milliliters to liters. So instead of 300, we're going to have 0.3 liters to divide by 1,000. And so 1.72 divided by 0.3 turns out to be 5.70 molar. This is much more concentrated than the previous two examples. We have had a half of molar. So anything over 1 is considered concentrated solution. There's a lot dissolved. And anything lower than 1, like a decimal place, will be considered dilute. In number 4, calculate the volume needed to make a 2 molar solution with 3.5 moles of lithium oxide. This one's little setup is a little different. We know the molarity, we want the volume, so you can put 2 molar on the left, 3.5 moles on the top of a fraction. That's over x. We don't know the volume. We'll have to cross multiply, so we get 2x equals 3.5, and then divide by the 2. So our final answer is 1.8 liters. The reason we want to know that is, let's say a lab requires 2 molar, and you have 3.5 moles on hand, you might want to know how much to dissolve that 3.5 moles in, right? So you're going to put it in a 1.8 liter of solution. So let's think about an example. If a glass of iced tea I made is too strong for you, what could you do to make it weaker, right? If it's just too sugary for you, which would never happen to me. I love sugar. But I think the obvious answer is that you're going to add water. And this process is known as a dilution. And it's very important in chemistry because we often purchase large quantities of highly concentrated chemicals because it's just cheaper in bulk, just like Costco or BJ's. And in order to use the chemicals in class for labs, teachers must dilute the chemicals so they're not as dangerous. Also, the highly concentrated things can wind up just burning through your other chemicals instead of actually reacting with them. So a dilution is a procedure for preparing a less concentrated solution from a more concentrated, or what we call a stock solution. And the formula we tend to use in class is M1V1 equals M2V2, something you should have seen last year. Note that that's not on the reference table, so if you want to squiggle it in for quizzes, you can. But when tests come and I give you a clean reference table, you'll have to know it. Or you could actually do the calculation using just the molarity formula, but you have to do it twice. One for the first concentrated solution, and then again for the dilute solution. So this is just a way of making the math a little bit quicker. Here's an example. 240 milliliters of a 3.5 concentrated solution is diluted to 300 milliliters. So we added 60 milliliters of water to dilute it. We want to know what the new molarity is. So it's definitely going to go down from 3.5. Your options are to just use the molarity formula. So you do 3.5 equals x over 0.24 liters and solve for moles. And then put those same moles into another molarity formula in which you have 300 milliliters of water. So it would be those same moles divided by 0.3 to find the new molarity. So you'll be doing two calculations in which the moles are the same because the moles haven't changed. You haven't changed how much of the solute, which they didn't even tell you what it was, right? They didn't. So you didn't change the solute, only changed the solvent or water. But the quicker way is to use the M1V1, and with the V, you can use any volume you want. It doesn't have to be liters, so it's really convenient. So I just do 3.5 M and 240 milliliters, or V, equals the unknown M, molarity, and the 300 milliliters, again, the V2. And then I can just multiply 3.5 by 240 divided by 300. We get 2.8 molar, and as predicted, the molarity has decreased because we added water. In a second example, we have 7.8 liters of 2 molar concentrated solution diluted by adding an addition of 10 liters of water. A key word here in this question is by the addition of 10 liters. So some people make the mistake of setting up their M1V1 by writing 7.8 times 2 equals 10 times x, right? The problem is we added 10, but we already had 7.8. So technically the setup is the 2 molar times the 7.8, what you should initially had, equals the unknown molarity times 17.8, and that's found by adding 7.8 to the 10 liters. So it has to be a total volume in order to get your total molarity at the end. But otherwise, we multiply the left and divide by 17.8, we get a 0.88 molar, and we see again that the molarity decreased over time because we added water. A third example, what volume of 9.3 molar H2SO4 is needed to obtain 450 of 2 molar? A very common question where in the stockroom you might have something very concentrated, 9.3 molar, burns your skin off. but in the lab you only want to use a 2 molar solution, which is a little bit easier to work with. So how much water, how much of that crazy stuff do you need to add to the 450, right? So we're solving for volume this time, and it was the initial volume. So I want to know initially how much am I going to grab of the 9.3 in order to get 2 molar 450 milliliters. We're going to multiply the right side and divide by 9.3, and it says 97. So I'm going to use a cylinder and grab 97 milliliters of the crazy stuff, probably with gloves on. I'm going to add it to a bigger container, and we're going to add water into it until it hits 450. In our next example, what happens to molarity when water is added? As we can see, the molarity always decreases when water is added. What would you have to do in order to have the molarity increase? Well, I hope an obvious answer is we would have to take the water out, and the only way we can really do that is by heating it and evaporating the water. And in some cases, you really don't want to do that because either the substance is flammable or maybe it's acidic, right? So another option would be to try to take out the solute. But I want to think about that. If this is dissolved in, can filtration do that? No. So I don't know how we would take out more solute. I think we're kind of stuck with let some of the water evaporate and maybe slowly over time. So either molarity increase. Yeah. Oh, increase moles. Yes. We can add more stuff in. So some more dilution questions, but these ones are more specific to what you're going to be doing in AP. A lab calls for 100 milliliters of 3 molar hydrochloric acid per pair of students. The stockroom has a large amount of 12 molar hydrochloric acid and 1 molar hydrochloric acid. Which acid are you going to use to set up the lab? It's going to be really difficult to get the 1 molar HCl to reach a 3 molar HCl. Not only that, but you'll be evaporating water, so you will have less solution over time, right? It will be less milliliters. So I think we're going to be using the 12 molar solution. It's easier to add water to it than to evaporate water from the 1 molar. And in question 2, the classroom has 26 students. Explain how to create enough of the 3 molar HCl for the lab and use calculations to support your answer. I would recommend pausing the video to do this. So what we know is that we want a 3 molar solution, and we need 26 students worth, but they're working in pairs of students. You go next to number 1, so we really just need 13 amounts of them, and each of those need 100 milliliters. So we need 13 hundreds, right? So I showed it as 26 divided by 2 times 100, but really you can write 1300 if you like, times the 3 molar. But we're going to use a 12 molar stock solution, so it equals 12x, right? So we don't know how much to use. When I solve it, I get 325 milliliters. So after that, what we're going to say is, in words, I'm going to obtain 325 milliliters of the 12 molar hydrochloric acid in, let's say, a cylinder. We're going to pour it into a larger flask, and we're going to add water until it hits 1300 milliliters. Some of the things that we want to say are really specific. So if a question asks you how to dilute a solution, make sure that you mention, and you should probably write this down, that you measure the amount of water needed using a pipette, or if that's not available, you'll have to use a cylinder. Never a beaker. Beakers are really just placeholders. And then place it into a volumetric flask, because this is the most accurate piece of glassware we have, so you can get a really specific dilution. Start with the highest molarity of the solute and measure this concentration with the pipette or cylinder. So take that highly concentrated substance and measure it with something that is really specific. Always add the acid to the water. The acid is more dense and will sink to the bottom, resulting in less splashing, so it's more safe. And can be added slowly because sometimes there's heat generated, and you can do it slowly so there's not too much heat. So question of the video, what we have so far is we know that concentration can be calculated in molarity. If there are 3 moles for every 0.275 liters, notice I changed that to liters, I can get a 10.9 concentrated solution. If I want to know how many grams that was, I would have to multiply that 3 moles that we just decided on by 58.44 grams on the reference table to get 175.3 grams. So that means I put 175.3 grams in 275 total volumes of water. How many particles are there? Well, again, we can go to that 3 moles, so you can see how important moles is right now, right? It gets us everywhere. It's the central hub. By 6 times 10 to the 23rd, because that's our molecular number. And we would say we have 1.81 times 10 to the 24th particles. So this is not an accurate picture, right? Remember, it was a representation. And would we need the same amount of sugar? So I'm going to go back to the fact that we wanted a 10 molar solution and a 0.275 liter solution. And so we know this is going to be still 3 moles of sugar. and 3 moles of sugar will still have the 1.81 times 10, to the 24th particles dissolved in it, but will have the same grams. So going back to the fact that you take the 3 moles and multiply the grams of sugar, which is a different substance, and weighs 180 when you add up C's, H's, and O's, we get 540 grams. So you need a lot more mass of sugar in order to equal the same amount of particles.